We're doing a deep dive today on regenerative civil design, and the focus is maybe not what you'd expect. A car park in St. Albans, Victoria.
That's right. It started as a pretty straightforward job for the Department of Transport and Planning. Just a layout tweak.
Yeah, just redesigning a car park layout. But it went sideways, didn't it? A simple infrastructure project derailed by, of all things, drainage failure.
Exactly. And it forced a really novel nature-based solution.
But the seeds of the problem were sown right at the start, yeah, with the initial constraints.
Absolutely. So the goal was simple enough. Reconfigure the St. Albans Hotel car park after some land acquisition for rail separation works. They just needed to bump the spaces slightly from 279 up to 285. Seems minor.
Okay.
But the critical constraint, the kicker, was in the detailed design. It explicitly stated they had to assume existing surface levels would remain. And crucially, no additional drainage. Existing drainage only.
No new pipes, no pits, nothing. Use what's there.
Precisely.
Yeah.
And that assumption, that constraint, well, it basically set the stage for the crisis that followed. It was a ticking time bomb.
And it didn't take long to go off, right?
Yeah.
The civil works finished in 2019.
Yep. And by 2020, the alarm bells were ringing. The new garden beds, they were just failing.
Failing how?
We're talking soil liquefaction. The native soil just couldn't drain.
Liquefaction. That sounds serious, not just muddy.
Oh, much worse. It means the soil loses all its structure, its strength, because it's completely saturated, like quicksand almost. So, any trees planted in these new garden beds, they're basically sitting in this dense, waterlogged sludge.
Ah, so they couldn't establish roots. They'd just drown.
Exactly. Successful tree establishment was deemed highly unlikely. The whole planting aspect of the project was in jeopardy. The client had a mess.
So the big question then.
Yeah.
How do you fix waterlogging when the rules say no new drainage? What did they try first?
Well, the first instinct was the conventional engineering fix. A study was done, and it recommended, predictably, installing new drainage pipes. The plan was to use pavement boring drill horizontally under the existing pavement to lay the new pipes without digging everything up. Standard procedure, really.
Makes sense. Less disruption.
Usually. But here's the irony. It turned out to be impossible.
Impossible? Why?
The boring contractor got to site and found the new garden beds they'd just constructed were actually too small for their equipment to operate in.
You're kidding.
Nope. And not only that, the depth they needed to drill at was too shallow for the machinery they had.
So the very infrastructure they just built
Physically blocked the standard repair method.
Wow. They were completely stuck then, boxed in by their own work and the initial constraints.
Pretty much. The traditional pipe and pit solution was off the table. Literally couldn't do it.
Okay, so if conventional engineering hits a dead end, what's next? This is where the regenerative part comes in, I assume.
Exactly. This is the pivot point. They had to think differently. They proposed something quite radical. A vertical drainage system.
Vertical drainage.
Okay.
So instead of trying to pipe water away horizontally,
They decided to go down. The idea wasn't to fight the impermeable clay layer near the surface, but to bypass it entirely.
right, work with the site's geology, not against it.
Precisely. This vertical drainage system had two main functions. First, it created a sort of natural underground reservoir within the topsoil layer itself. This helped manage that initial inundation, that surface water logging, a buffer zone, if you like.
Okay, manages the immediate problem. But the water still needs to go somewhere, right? It can't just sit there.
Correct. And that's the second crucial function. It established a natural drainage outlet that directed the excess water vertically, straight down.
Down past the problem clay layer.
Yes, deep down into what's called the regolith layer.
Regolith. Okay, what's that?
Think of it as the layer of loose, broken up rock and soil material that sits directly on top of solid bedrock. It's often much more porous than the dense clay above it.
Ah, so the clay was like a bathtub liner, holding water in.
Perfect analogy. The clay was the liner. The vertical drainage essentially drilled holes in that liner, letting the water drain down into the naturally absorbent regolith beneath.
So it uses the deep geology as a massive natural soakaway.
That's the core idea. It bypasses the problematic upper strata and taps into the drainage capacity that's already there deeper down. It's biologically supportive infrastructure.
Okay, conceptually it sounds brilliant. But did it actually work? I mean, fixing soil liquefaction with vertical drains? It sounds unconventional. Did it hold up?
Well, the proof is really in the results over time. The remediation was successful.
Yeah.
There's visual evidence comparing the site. You look at photos from 2020, those waterlogged beds where trees were doomed.
Right.
And then you look at photos from, say, 2025. You see healthy, established, thriving trees.
So the trees that were highly unlikely to survive are now doing well.
Flourishing. It completely validated the approach. It showed this low-maintenance, long-term design actually worked in practice. It turned failure into success.
That's quite a turnaround. So wrapping this up, what's the big takeaway here?
I think the key lesson is that regenerative design isn't just a nice-to-have green option. It's a practical, sometimes necessary alternative when conventional engineering fails, especially when site constraints like budgets, access, or, in this case, existing geology and rules make the standard pipe and pit solutions impossible.
It finds ways to work with natural systems, like using the regolith layer for drainage, rather than just imposing artificial ones.
Exactly. It turns constraints into opportunities by understanding and utilizing the site's inherent natural processes.
Okay, so let's leave our listeners with a final thought then. If this kind of vertical drainage, this working with the geology, can solve soil liquefaction and save trees in a small suburban car park, what other impossible infrastructure problems can we tackle by shifting our perspective? Think about highway runoff, urban flooding. Could we solve more complex challenges simply by designing with the earth beneath our feet instead of constantly trying to pave over it or fight against it? Something to think about.